The eigenvalues and the eigenvectors, and more specifically the values, tell us very interesting properties about the matrix itself. So there's two properties that I want to review through that are pretty important. The first property is that if I have even if I have zero, okay, if I have a square matrix, the determinant of the matrix can actually be found by looking at the product of the eigenvalues. Okay. One thing I forgot to mention, by the way, this means product. This means eigenvalue 1 times eigenvalue 2, eigenvalue n. One thing I forgot to tell you is if A is an n by n matrix, then there exist n eigenvalues. Now, they don't need to be unique, but there's a total of n, so you could have repeated ones. So we can see from our last one, recall that we had the matrix 1, 2, 4, 3. Remember that? What's the determinant of this? 3 times 1 is 3, minus 4 times 2 is 8, which gives us minus 5. But if you remember, we had two eigenvalues, which were minus 1 and positive 5, which means we get minus 5. So that confirms it. We can very quickly and easily find the determinant of the matrix, assuming, of course, we know what the eigenvalues are. The next property of the eigenvalues I would like to mention is that of the trace. Now, what is the trace of a matrix? The trace is the sum of the diagonals, and some of these have, the trace gives us some interesting properties in and of themselves in more advanced statistical methods that I'm not really going to mention any further at the moment in time, at least. But the entire idea of the trace is just basically to add up the diagonal of the matrix. So as it turns out, when we add rather than multiply, when we add all the eigenvalues, which is, if you remember the notation here, we get the same thing as adding the diagonal elements. So here, notice we have 3 plus 1, where we get 4. I'm sorry, just make sure I have this correct. I believe I had a mistake. It's the absolute value of the added ones here. Right. I'm just making sure that my mathematics here is correct. Here, I think I have a mistake somewhere, but that's okay because we see this anyway, right? Take the addition of the diagonals and we get 4. Add up the eigenvalues, we get minus 4. So a slight discrepancy. I believe we just get, if you add up the absolute value of the diagonals, the values are the same. Anyway, that's the trace of the matrix. With this stated, as we can see, the eigenvalues have some very interesting properties, which allow us to very quickly compute certain elements, and what we'll see later as well. sorry, I'm just checking my math because -4, -5, main diagonal. Sorry, I'm just checking my notes here. The trace of the matrix is defined as the sum of the diagonals, which we have, and as far as the eigenvalues go, oh, this is why. Okay, they're not per se, because we have. Well, that's a yeah. Yeah. Sorry, I'm just making sure that my math here is correct, which it is. My math is correct. I don't know. Don't know why I'm getting negative here. But anyway, I don't want to hamper on this detail. Generally, it's true that the sum of the eigenvalues are equal to the trace, which the trace is defined as the sum of the main diagonal. But for whatever reason, I'm getting 4, and then I'm getting -4. Oh, no, I'm not. You see, this is the problem with the non-interactive stuff. I made a mistake. 5 minus 1 is 4. Hello. Okay, so ignore everything I said here. Trace of A is the summation of the main diagonal, which also the property is just not the absolute value, is just simply, I was right the first time. I just had made a small arithmetic mistake. Anyway, sorry, not to ramble on too much, but these are two very interesting properties of the eigenvalues and eigenvectors that will help us very rapidly compute things that otherwise take quite a bit of time.